Hi, everyone. We'll continue from Monday, okay? So Monday, we were discussing this algorithm and try to prove that this algorithm computes the product of two natural number x and y, all right? So as I mentioned, the main idea is we try to prove this loop invariant. And then when the algorithm terminates, because let's see, it's here. Because yi star is 0, so I star is the number of iterations, all right? So therefore, we have xy equals the value of t. So then we print out indeed equals xy. So if we can show that this relation holds after each iteration, then when the algorithm terminates, it's guaranteed that p indeed equals x times y, all right? So how can we prove it? The idea is to use induction on number of iterations. So we use number of iterations to prove that this one holds after each iteration. Okay. So of course the basis step. So let's see. So erase these things. So in the very beginning, we have x0 equal x, y0 equal y, and p0 equals 0. All right. So when I equals 0, so before the first iteration, I equals 0. So that's what we have. So of course, if we plug in, we get xy equals x0, y0 plus p0. So for these three values, indeed, this one holds. So for I equals 0, this one holds. We have to check this. Okay, initial condition is very important. But here it's very simple. We can either check. Indeed, this one holds for I equals 0. So that's basic step. Typically, it's trivial, but it's extremely important. We have to verify it for the basis step. All right. So now what we do is assume the loop invariant holds before the ith iteration. Then we show after ith iteration it also holds. All right. So here is the induction hypothesis. This is the point. Okay. All right. So what we need to prove is loop invariant still hold. After ith iteration. Okay, let me see if that's a problem. I'll just okay. Yeah, I'm correct. It's a PCR equals 0. No, not type of PCR equals 0. Did I write something else? Oh, actually, basic step is here. Okay. Okay, so let's erase these things. So that's what we need to prove if we want to use induction. So in the induction step, we use this assumption to show that loop invariance still holds after ith iteration. So what we do have is this one holds, so that means all right. So what we need to show is xy equal xi, yi, plus PI. So this induction hypothesis. Okay. So what we do, we consider two cases, because here we see in the algorithm, the execution will be different, depends on whether y is odd number or even. So here I will only consider odd case. Even cases is very, very similar. Actually, it's easier. So two cases to consider. One is even y, maybe not odd y, let's say, not odd y, and then odd y. Two cases. So when y is even number or y is odd number, two cases, 1, 2. All right. So here I will only consider this case. The other case is very, very it's very similar, so you can work it out by yourself. All right. So let's just consider this case. When y is odd, what happens? Right. So we consider this case. Okay. So let's see what happens when y is odd. So new value of p, so that pi equals, after execution will be old value of p, I minus 1 is old value, plus old value of x. So we have to see what happens. All right. Now for x is doubled. New value of x is twice old value of x. New value of y equals old value of y divided by 2 and take its floor. So it's y I minus 1 divided by 2. So that's what we get after one iteration. All right. After one iteration, new value of x, y, and p equals these values, the interim old values. All right. So from here and the induction hypothesis, we want to show that this one still holds. Okay. So let's see. Actually, it's just very simple manipulation of these formulas. So let's see. Okay, I need some so xi, yi. So we just use 2xi minus 1 times yi minus 1 divided by 2. Okay, so that's 2 and 2 cancels. Oh, sorry, here the I minus 1. It's on here, the I minus 1. It's a typo here, I minus 1. Okay, so here, what we get is xi minus 1, yi minus 1 minus xi minus 1. So that's what we get, all right? So here we get xi, yi equals this one. All right, now it's very simple. Replace this one. Xi minus 1 equals, let's see, pi equals this one. Okay, this one, if we move it, so this one minus this one, if we look at this one, we get pi minus 1 minus pi. Okay. Now, if we shift it over, what we get is xi, yi plus pi equals xi minus 1, yi minus 1 plus pi minus 1. Now, here, this one is induction hypothesis. So which equals x1. By induction hypothesis, this one equals x1. So therefore, that's what we get. So we see loop invariance still holds after IC iteration. Okay. Same by principle in mathematical induction. That means after each iteration, regardless of the number of iterations, this will always holds. Of course, number of iteration will be basically in the order of log 1, phase 2. This one, okay, maybe it takes the ceiling. Okay. So after this many iterations, it stops. So that I stop. But after each iteration, regardless of number of iterations, this one always holds. So when y becomes 0, we have this part is 0, therefore p equals xy. So that's how we prove it by using mathematical induction. All right. So that's case for y is odd. For even it's even simpler. Okay. So I will not show you the even case to save time. The key point here is the most difficult part actually is in loop invariant to come up with this one. To come up with this one, that's a hard part. That's hard part. Once we have it, the rest is just very simple manipulation of algebra. Of course, sometimes maybe not straightforward. In this case, it's rather straightforward. But the difficult part is really to come with loop invariant. We have to find a relation that will enable us to get our conclusion. So here P equals xy when algorithm terminates. So we get relation between xy and P. And also in terms of immediate, the intermediate values of x and y. All right. Okay. All right. So I give you 2 examples of proving correctness of algorithm. It's not easy at all. For frankly speaking, most of you may not need to prove correctness of algorithm, even in your clear life. Most of them you maybe just do application. For you, perhaps you do just testing and debugging to get a program. But for people who want to do theoretical computer science, then you do need to prove correctness. But even for some people, you may need to prove the correctness of algorithm for some algorithm. It's very difficult. To be honest, it's very difficult, not easy at all. I just want to give you a taste of how to prove correctness of algorithm. So for some simple algorithm, I hope you will be able to get an idea and to do it by yourself. For other difficult algorithm, it's very, very difficult, not easy at all. Okay. So here are the simple examples. All right. Okay. Now another point I want to make, actually the very foundation of this one is what we are doing when we're proving the correctness. Again, is this word, recurrence. Actually, our proof is based on recurrence. Now it's not explicit in the algorithm or in our proof, but actually both our proof and algorithm are based on recurrence relation. Okay, so I want to point it out. This algorithm and the proof are based on the following recurrence relation. Once I give you a relation, actually you will have a better understanding of this algorithm, of course, the proof. All right. Now the recurrence is very simple recurrence. Okay. So this function represents product of xy. Actual product of X and Y are basis reference. Then initial condition is y equals 0. Oh, sorry, y equals 0 is 0. Let me see. Should I do? Yeah, it's okay. Y. There are two possibilities. So 0 or x y equal 1. Okay. Either way we'll do it. Okay. So here actually go to 0. So it can be 0, 0 or 1x. Okay. So this will also work, I think. This one. 0 y equals 0. This can be used as the initial condition of this one. All right. Now, whenever y is even number, so product of x, y is same as product of 2x times 2y. Of course, it's quite obvious. We have this equality. All right. Otherwise, if y is odd, what we have, I want to leave it. Actually, to here as well. Xy equals 2x times y minus 1, 2 plus x. So this one, it's related to this one, okay? So we have equality for these two situations. So actually, it's a defined reference for product of two numbers. So the algorithm and our proof really based on this reference relation. You will see when it's odd, we do this one. So here plus here. When it's even, we don't have this one. We only have these two. Okay. When it's odd, we have both this one, so this part, and the plus x and this part. All right. Okay. So please spend some time afterwards to really understand what's going on for this algorithm and the proof associated with this algorithm, to really understand how we use induction to prove the correctness of the algorithm and why this one works to compute the product of two natural numbers. All right. Okay. So I finished the discussion of inductions. Later on, you will see induction again and again when we want to prove things related to natural numbers. All right. So again, importance of recurrence here, recurrence. So this is a really very important concept and very, very useful. Okay, recurrence. Now, once we have a recurrence, what we need to do with the recurrence, of course, we can use it for computational purpose. But recurrence itself sometimes is not good enough for us to get what we want. For example, I give you Fibonacci numbers, Fn. Okay. So let's see this recurrence relation together with these two initial conditions uniquely determine a sequence called the Fibonacci sequence. So with this definition, we can easily compute a Fibonacci number. It takes time, of course, okay? However, this may not be good enough in order to understand or satisfy our need. For example, suppose I ask you to, maybe tomorrow I ask you to bring me, say, F10 coins. So what do you mean by F10 coins? So you would like to know what's the value of the actual value of F10. All right. So one way, of course, we can use this reference to compute this F10. But it may be even better if we can have a closed formula for F10, for Fn, maybe close the formula. Okay, because let's give a better understanding of this number. If we have a closed formula, for example, how big is this number? How fast is it closed? Is it a linear function of n, or quadratic function of n, or an exponential function of n? Without knowing a closed formula, it's hard to tell. Of course, from experience, one can tell. Maybe you can feel this one is an exponential function. Okay, but in general, normally it's very difficult to tell from the current how fast it goes. What's the value of this one? So it will be better if we can close the formula for f of n. So that's called call for solution of a recurrence relation. We want to solve a recurrence relation. So what it means is we want to find a closed formula for this, for its value, for the nth value. All right. In general, it's not easy at all, but there are conventional ways in order to solve a recurrence. So we can start with basic techniques. Then we'll get into tools for solving recurrence relation. For that, we'll give a template for solving these things, give you formulas for solving them. Okay, but before we get into this, let's consider recurrence relation. So an equal to an minus 1 minus a and minus 2. So consider this recurrence relation. Now, actually, many functions can satisfy this recurrence condition. For example, we can have an equals 3n. Or we can have, it's not unique at all. An is a constant, it's 5. It's always 5. Okay. Both will satisfy this recurrence relation. Now, in order to satisfy a recurrence relation uniquely, we have to do initial conditions. Once we have right number of initial conditions, then the recurrence relation can be determined uniquely. So the recurrence relation alone may not give us unique solution. We need the recurrence relation plus initial conditions. To uniquely determine a sequence. A sequence. All right, so for example, for this sequence, depends on initial condition, the result will be different. So initial condition is the, suppose I have A0, A1. If both are 5, then the solution will be an equal 5. It's always a constant. If it's 0, 3, then the answer will be 3n. The sequence is 3n. Okay. Now, if it's 1, 3, then it's 2n plus 1. Okay, let me check. Yeah. Okay. So initial condition together with recurrence then uniquely determine the sequence. So it's very important. We should not ignore initial condition. Even if we have recurrence, we still need the initial condition to uniquely determine the sequence. So that's very, very important. The number of initial values depends on recurrence. So here it depends on use 2, n minus 1, n minus 2. So we need 2. Okay. Suppose I change it. Let's change this one. Say to 4. So here only involve 2 previous terms. Number of initial condition, how many do we need? Not 2, it's 4 here. Number of initial condition is 4 because in order to get this number, an, I need these 2 numbers In order to get this number, I need this number and this number. Okay. Now, these two, I also need them because I cannot compute this one from previous one. So if this one is A4, A3, say, okay, so let's start with 0, A3. Then A0, oh, it's A4, sorry. Yeah, A4. A1, A2, A3. These four values need to be given. Because I don't know how to compute these two values from the previous one. It starts here. In computing A4, these are not needed. But when I compute A5, A1 will be needed. Compute A6, A2 will be needed. All right. So be careful with number of initial conditions. Number of terms we need depends on reference. Depends how many previous terms is needed. Okay. All right. Okay. So how do we solve a recurrence relation? The very basic method is use iteration. Okay, so what we do is then try to find a pattern and guess a formula. Of course, that will be educated guess. We guess the formula. Now, if we really guess formula is guessed, then we'll need induction to prove it. You see, again, induction comes into play. So they really come together. Okay, now the third step, whether we need it or not, really depends here how we guess it. If really we guess the formula, then we do need induction to prove it. But if not really a guess, it's a very, very well-educated guess. Actually, it's not a guess, but we really obtain the formula from the pattern, then the step may not be needed. It's not needed. Okay. I will give you example to illustrate that. Now, another important thing is when we compute a few terms, don't simplify it. Don't simplify the pattern. Okay. So that's the basic idea. I will give you some examples to see how we use it. So here's just a guideline of how to use iteration method to solve a recurrence. Okay. All right. So let me start with the following game called the Tower of Hanoi. Some of you may have seen this game. So we have 3 packs. Okay, so at the end this pack A, they arrange assorted. The largest one on bottom. So here I show you 4 discs. your task is move all the path and all this from A to C. One disk at a time. And also in the process, you can never put a big disk on top of a smaller disk. Okay, smaller disk should be always on the big disk. So if I could move this one to C, then I cannot moving a remaining disk to C. Once I put it here, so I can do nothing. So that means we have to use disk B as a buffer. So I can put this disk here. All right. So then I can move this disk here. Then I can move this disk over, doing like this. So the first two disks will be transferred from A to C. Okay, so that's how it works. All right. Now it turns out, in order to move n disk from A to C, so number of movements has the following relation. So if we use Mn movements for n disk, if there are one disk, of course, only need one move. Okay, otherwise, it obeys this relation 2m n minus 1 plus 1. It has this reference relation. Okay, why? Let me explain to you why. Now, in order to move n disk from A to C, what happens? Eventually, this disk should be moved from A to C. So, in order to move this disk from A to C, Cn minus 1 disk needed to be moved from A to B. So that will be Mn minus 1 moves. All right. After that, I can move this disk to C. So this disk goes from A to C. That's one move. Now all these disks will move from B to C. So that's another n minus 1 move. So that's why it's our basis reference relation. So twice n minus 1 plus 1. All right, so we get this reference. All right, so let's see what's the number of movements. There fairy tale associated with it. It's 46, I think. Once you can finish it, then the king will give you, will allow the handsome young man to marry his daughter or something. Things like that. 64 discs. Okay. So once we solve that, we see it's an impossible task because this number grows very fast. You cannot finish it in your lifetime. Okay. All right. Now we can forget this background to see how we can solve it. So using our idea of iteration method, what we do is extend a term. One way is we start with 1. Okay. Now n equal 2 will be 2 times 1 plus 1. So n equals this n equal 1, n equal 2, n equal 3. Okay. Now for 3, it will be twice times 2 plus 1 plus 1. That will give a 2 squared plus 2 plus 1. Okay. Now the note I made, so the remark I said and made, you don't simplify this. So here we should not simplify this. This one equals 3. This one equals 7. It's not good to do it this way because once we simplify it, we may not be able to see the pattern. So it's better to keep it in this form, then we see the pattern. All right. So don't do this simplification. Rather, we keep it in this form. Okay. Now 4 will be 2 times this one. Will be 2. Now, do you see a pattern? So see, the pattern is 2n minus 1 equals 2. If we keep on doing things like this, so it seems this one is this. All right, now we need to do summation in order to find the closure formula, the summation of this one. So it's mn equal to n minus 1. Okay. Now, if we do it like this, we get the patterns, and we'll need to use induction to prove indeed this one is the solution. But this pattern, you are quite confident we have to have this one. This pattern from here, you're quite 100% sure from here you can get this one. Then no need to use induction to prove it. Depends how you get this pattern. If you get this pattern from these are few terms, then it's better to use induction to prove it. But rather, if we really prove this one equals this one, so it's from this, not really from this pattern, but from this pattern, you're able to conclude indeed this one equals this one. Then there is no need to use induction to prove it. All right. Now, actually, there are best way to organize the argument here. Extend a few terms. Actually, if we do another way along, maybe it's better. Then we'll get this one directly. Let me show you how we do it. Okay. So it's easier to organize things in this way. All right, so that's the value we want to obtain. Okay, so it can be expressed as this using the translation. Now for this one, for this term, we write it this. So again, this one, mn minus 1 equal to n minus 2 plus 1. So you use the translation. So that's what we get. All right. Now this term, we write it this way. So multiply this one, both sides by 2. That's what we get. All right. So keep on doing. Let me do one more term. Okay, so eventually, what we get m2 equals m1 plus 1. Right? Eventually, it's a backwards. Initially, when we get pattern, we do it in this way, but now we do it in backwards. All right. So here will be m2 equal m1 plus 1. So here will be 2 here. All right. Here will be 2 here. All right. Now, what's this number in order to get this 2? So n minus 3, this one becomes 2. So from this one, it's 3, 3. Let's see. Sum of this one and this subscript equals n. So when it's 2 here, n minus 2. So when the n minus 2 here, 2. The summation equals, let's forget about this one. Okay. It's easier to see this. So sum of them equals n. So here it's 2, then n minus 2. All right. So here is n minus 1. So here is n 2. Let me think. This is n minus 2. So this n minus 2. Okay, we can organize things in this way. Then we take summation of both sides. Then what happens is these things closes. All right, now we get exactly this one. 2n minus 1, n minus 2, up to 1. We get this one. Now we do summation. we'll be able to obtain this result. This solution, this is our solution. So you see, number of movements grow very fast with number of disks. It's the exponential function of n. All right, okay. So that's first example. Let me do today. I guess I only have time to do one more video. Maybe two. Okay, let's see. Maybe two. Okay. So let me do another one first. Let's consider a number of ways to group 2n people into pairs. So if we form people A, B, C, D, we want to find different number of ways of grouping these people into pairs. We can group as AB and CD. We can do AC, BD, and so on. So we want to find a number of different ways to group 2n people into pairs. So how can we do it? All right. Suppose we use this number, so Pn, to denote this number. If two people, so n equal 1, only one way, because two people. Okay, so if otherwise, n is 2. So how can we group 2n people into pair, number of different ways? So for a particular person, how many different ways can we pair it up? It can pair up with any of the remaining 2n minus 1 people. So there are 2n minus 1 people for a particular person. We choose one person. For this person, there are 2n minus 1 different ways to pair it up with other people. Okay. So once we have done this pairing for a particular person, then the problem will be Pn minus 1. Number of ways for grouping 2n minus 2 people into pairs. So that's the reconciliation we have. All right. So for this one, it's quite easy. We can just do a few terms. So P1 equal 1, P2. If we extend a few, we'll see the pattern. P4 equals 7. So it's a product of first n order numbers. Okay. We can always also extend it from here, n equals 2n minus 1. So here, this one will be 2n minus 1 minus 1. Of course, that will be 2n minus 3. 2n minus 3. Pn minus 2. So it's carry on, we'll get 2n minus 5, Pn minus 3. And so on. Okay. So that will be 2n minus 1 times 2n minus 3 up to 1. Product of first order numbers. So that can be rewritten as 2n minus 1 factorial times 2 to n factorial 3. Also 2n factorial, should be 2n factorial, so not 2n minus 1. Can be using factorial notation. It looks like this. Oh, okay. Time is up. I thought I have time for another example. But anyway, we'll continue next week. Okay, best stuff. So get the basic idea. I will give you 2 more examples next week. Okay, about the iteration methods. And then we'll get into formulas for solving the reconciliation, for special type of reconciliation called the linear reconciliation. We do have formulas. So that's what makes things easier. Like Fibonacci number, we can find the solution using formula method. All right. Okay, that's it for today. Funny. One thing I want to mention is a midterm exam. Okay. Because there are 4 sections, we are coordinating the time. It haven't been decided yet. it will be towards the end of October, maybe last week of October or first week of November. It haven't been decided. Actually, personally, I even want to get rid of midterm exam, but I don't know because it's not my own decision. There are 4 different sessions. Somehow they want to coordinate it. Okay, so I'll let you know later. All right. Okay. Also, I will post second assignment latest by tomorrow. I think I should be able to get it done by today. Okay, so you can enjoy assignment 2. All right. So thank you. That's it for today. This one should be bad tendencies. The bad tendencies is here, Tony. Otherwise, yeah.